Okay.
This is just silly. It's not the title of the talk is this.
Yeah. So, will you explain what a moose is?
Yes,
Okay. New animals for us. You know, we don't have them here.
I know.
Okay, Olivier Bilodeau from Canada. Is that? Yeah.
Represent.
You have the floor.
So I presented about IoT in a local conference in Quebec in French called Hackfest. And so I had one of my colleagues from ESET, Marc Etienne, did a nice fake Shutterstock photo for the talk, which I decided to share because it's featuring the cyber theme and has French in it, and also mentions shell shock photos instead of Shutterstock photos anyway. So just a little aside here. So today I'm going to present about Linux Moose, which is an embedded Linux botnet. The agenda will be embedded Linux malware. In general, just a little bit of the description. Moose DNA, so description of the malware, the operation, and then a few updates, what's new regarding this botnet, and some takeaways. Throughout the presentation, it will be sprinkled with lessons learned of our story, if you want, looking and investigating this botnet, and also some design decisions that we will highlight of the done by the malware operators, good and bad. Also some code snippet. We shared a lot of our code for this research on GitHub, so we will plug it. And so yeah. So before we dive into the subject, why am I here? So I'm a malware researcher at ESET. I switched jobs since then. I work for GoSecure now, which is I starting a new research department in this small Canadian company. But all of this research was done as ESET and is presented as ESET. I did some lectures at ETS in Montreal. Also, I was before involved a lot in Linux systems as an InfoSec developer, network administrator for core internetworking at Bell Canada ISP, and Linux sysadmin for Bell also. We have a few things in Montreal which are worth of mention if you ever come by Montreal, which is Montreac, which are hands-on security workshops, so 3 hours of hands-on CTF solving challenges. And also, I do the NordSec Hacker Jeopardy every year, and I'm also in charge of the NordSec trainings. So if one of you is a trainer and still has time and doesn't leave right after the conference, come and see me. I might be interested in having you give a training in Montreal. So what is embedded Linux malware? What marketing or the internet as a whole likes to call Internet of Things malware? Well, basically, it's malware running on an embedded Linux system, right? Nothing to learn here. So what kind of embedded Linux system? Mostly consumer routers, but some DVRs, some smart TVs, IP cameras, etc. A lot of stuff. What are the characteristics of embedded Linux systems? Well, there is not a lot of memory, not a lot of flash. Rarely there is a hard drive. Usually it's not running on x86 architectures, so ARM, MIPS, some PowerPC, Super H. There's a wide variety of libc implementations and version. You can have it's like almost never the GNU libc, which is there. It always using a Linux kernel, well, because it's an embedded Linux in this case, the specific case I'm covering today. Which is very important is that the ABI is compatible. So syscalls are always compatible, which means that, as we'll see later, we rely on this to do statically linked binaries, which make reverse engineering a bit more complex because there are a lot of code to look at. It supports ELF binaries. There's rarely a UI, and it's networked. So attractive because there would be a lot of potential victims. Also, maybe what I should have added here is that security usually is an afterthought in these systems. It's not really designed with security in mind. So why threats on these systems matters? Well, as I mentioned, there's no UI or rarely a UI besides a web interface, which means that it's hard to detect and also hard to remediate. Hard to have access to the system and do some like computer type task unless you solder pins and you get access with a serial connection on it. It's hard to fix problem also. Vendor updates are non-existent or mostly inexistent. And right now, it's been a low-hanging fruit for bad guys. If you put something listening on telnet port on the internet, you will notice that there's a lot of things going on trying to attack routers on telnet port with default credentials and then push binaries and leverage your device. So it's real also. Several cases were disclosed in the last 2 years. A lot of the same stuff, so DDoS mostly, some Bitcoin mining, but they soon realized it was not efficient to do Bitcoin mining on consumer routers. And things are only getting worse. So just a few of the things we saw if you've been watching this space for the last months. Sality had a DNS changer named Win32 rbrute, which a colleague of mine, Benjamin, talked about, which is so related to the Sality malware that was the previous presentation. Other stuff found by Avast, so hiding with an embedded rootkit. Also, the Lizard Squad group was found to use embedded malware to do DDoS, so controlled by a panel, but still running on which it's called Laser Stressor. Also, lately there was for a virus bulletin, Symantec published about YFatch, which was a vigilante worm of IoT, which was cleaning the other infections. And lately, we saw that it could have future targets like the Hello Barbie, which has Wi-Fi and which has been proven to be insecure already. So no malware, I think, yet on this one, but it's definitely a future target. So we say IoT, but is this really about things right now? So no, the point I want to make here is not yet. IoT has been mostly collateral damage. So that's why the focus of this talk is embedded Linux, which is, I feel, more accurate description of where the malware is. So what is affected? Again, leveraging the network capabilities and the position and the weak security is consumer routers, or how I would prefer to present them based on their security, a ton of crap. So I understand it's not that great, security is not great, there's market pressure and everything, but still things will have to change, and they started changing, which is good. But the industry, or I don't know, something will still have to improve. For example, admin as a password. Things will have to change because right now there is Caffeine blogged about a CSurf payload which leveraged so kind of defeating your firewall, going to your router from the inside, and then changing your configuration, your DNS configuration, which means that if you can randomize the password for the WPA key, randomize the password for the admin, please. Stuff like that, So what kind of malware can we find on such insecure devices? This is a list of the stuff I looked at while looking for a new version of Linux Moose. Here you can see that Lizard Stressor is actually GetGit, which is more or less clear if you read Krebs' post, but is clear when you look at the binary. But these are all mostly forks because they had access to source code, so they all copy each other and add their own thing in it. With this behind us, let's dive into the Linux Moose story. So first thing we learned analyzing Linux Moose is the statically linked strip binaries. So statically linked means that the libraries are inlined into the binary, and strip means no debugging symbols, for those who are not familiar. So no imports means everything is inside, and everything is bundled down to the kernel syscall. And the disassembler, even if you have one, so even if you have the big ass version of IDA with the ARM disassembler, it doesn't help you because there is just a ton of C code and nothing makes any sense beside the syscalls, which are hard-coded and which IDA doesn't even map. You need to look at the .h file for the Linux kernel and then manually or through an IDA script map them. So just to give you a sense, this is how the Linux Moose binary looks in IDA. So this, as you can see, we see in those 3 pages 33 lines of functions out of 500 functions. So this is only the beginning of the whole thing. Now, the code is not simple to analyze. Let's take as an example if you try to debug the printf, just so you get a sense of how complicated it is to deal with statically linked strip binaries. So this is the printf family of calls. In this, there is no syscall that are directly. Everything will go through the put syscall, which is really deeper in the thing. So this small piece of the proximity graph of IDA is part of this larger. As you can see, the pattern in the middle. So this is still all printf and not functions, but group of functions. And you can see the vprintf internal. So most of the external interfaces, snprintf, sprintf, are all calling at some point underscore vf printf internal. This function, we have to go deeper to reach it, is looks like this. So again, I want to stress that this is all. There is no single syscall in this code. So you're not sure if you are in malware code or if you are in library code at this point, unless you know your printf implementation by the look of its graph. And so you have to look it up. The ecosystem makes it even worse because the libc are always changing. So compiled binaries will change often. And the IDA flirt signatures for these type of architecture it never worked in all the samples I looked at. So there might be some tricks, I don't know, and I'm open to suggestions if there's any. Also, there are various C libraries. So you have muc libc, ajlibc, glibc, muzzle, and a lot of other C libraries, which again, any binary which you have C code can be linked against, and so it would have you start your analysis from scratch if it's a different C library. So the lesson that we learned here is what we tried at first to map the syscall with an IDA script, but there was still too much code to reverse engineer because, as the example I just gave, going back through the put syscall up to the printf, we were still not sure in which part of the code we were. Were we in malware code? Were we in a printf? It wasn't clear. So we still provide the tool just in case if anyone wants to use it, but we found a better solution. So what we did is we reproduced the environment, so the architecture, libc, and compiler version. We built libraries with symbol under the same condition, and then we used bindiff to map library functions. And then we were able to focus on malware code. So it sounds easier than it actually is. But maybe not. Maybe we think we're clever, but we were not. It's actually Mark Etienne's idea, another colleague at ESET. And here's what it looks like. So in this specific case of Linux Moose, we used uclibc 0.9.33, which we compiled using the OpenWRT toolchain. So this is probably what the malware author are using to compile the solution. More than 225 functions were mapped with a high confidence and high similarity rating. So we didn't even have to think about oh, should we import it or should we look at it? 225 were done select all and then just import. And so stuff like strncompare, fgets, inet, nettop, openzir were all straight imported into the Moose library, and so it really helped us kickstart this investigation. So the lesson 0 is going down to syscall is too long in large binaries. Find a close match of your C library, build it with symbols, and then bindiff it. Or maybe we could have flirted at this point, which is something I'm not familiar with. This is why we went with bindiff since we had licenses and we were comfortable with it. Another lesson that we learned is be careful of strings and AV variant names. So in the specific Linux Moose case, the AV variant names were all, it might be a little bit small, so I'll spell it out. Bitcoin miner or Bitcoin miner related, ESET had agent.p. But so when we first look at it, we were like, okay, so this is a miner thing. So we were really looking for Bitcoin mining features in the binary, only to realize that it was killing Bitcoin miners inside the feature set of the malware. It was actually looking for processes of Bitcoin miners and killing them. And it was flagged as other AV as a Bitcoin miner because of those strings, which again is a misclassification. So everyone gets bad intel. We think it's a miner, but it's not actually. Another thing that happened is we found a host name inside the strings. at some point we were collaborating with external entities on the research, and they told us after the fact that they requested a takedown on the getcool.com domain, which is in the strings that is here. And so I was like, first, this is not cool. I share you a sample, and you go and take down a domain without asking me first. Not cool. And which, like, it was funny because in the end it turns out that this was completely unrelated. It's a fixed host header used by the malware. So the lesson again is, be careful with the strings that you see, and also don't do stuff or take down based on other people's research. Please get in touch first. So now going into the design of the malware. First, thumbs up for the malware operators. Misleading strings. It creates confusion in the industry. Good job. Now, if we look at the DNA malware description, the gory details of this are all in the report that we released in May, end of May. But we'll summarize some of it. So Linux Moose was discovered in November 2014, thoroughly analyzed in early 2015, and we published a report, as I just said, in late May. And then after, I went to Recon, and it was BotConf CFP right after the Recon hangover. So I was like, oh, cool, I never presented this nowhere. I need to write the CFP. That's why I'm here. So Linux Moose, just get this out of the way. Why Moose? Well, it's named after a string, elan, present in the malware executable. Elan is French for moose, so élan, which I would say in French. Élan, élan. So there's the French Canadian. French Canadian is élan, et élan in the French. Which is this animal. And so I know you don't have around here. I don't think there's many. But after we released the paper, some other people had better ideas for the élan string, which was the Lotus élan. So thanks to internet crowdsourcing. Or also there is a Slovak rock band from the 70s, late 60s, called Élan. Hat tip to Robert Lipovsky for this less obvious reference for Canadian. But joking aside, the sample itself is a statically linked stripped ELF binary. We found ARM, the two variants of targeting two ABIs, and MIPS in both little and big endian variants. We found absolutely nothing, no x86 sample. So no X-rays for us. And the CNC IP was an integer form buried in the code. So no strings to reveal the CNC IP like most of the Lizard Squad stuff still has. So thumbs up. MIPS ARM, statically linked, strip, no x86. Good job. It took a long time. Bad job. The strings were not obfuscated. You can do better next time. So on a more serious note, what are the network capabilities? It can pivot through firewall. So it's infecting routers, so the routers are besides the network. And it has a stun type NAT traversal capability. So if you have a telnet listening host, it could, even if you are firewalled like DMZ style with like no outbound access, it could use rendezvous of itself if you want, like kind of peer-to-peer, to get deeper into your network. Stuff that we didn't see really in use when we did the analysis, but it's possible by the design. There's also a custom-made proxy service. This is the main payload that is used by the criminals. And the proxy service is only available to a set of authorized IP addresses, which are decided by the CNC. So there's no way to fingerprint the internet because of this list of authorized IP. Any connection that is not in that list will simply get a closed port. And if you scan on it's by the way listening on a specific port, which is 10,073. So if you scan the internet on this port and you see any firewall which do a close, it will have the same behavior as this proxy if you're not authorized. So there was no way for us to map population of the botnet using that feature. It also has a remotely configured generic sniffer, so it can sniff traffic, and the strings that it's interested in are provided by the command and control server, and it has DNS hijacking features. So lesson learned number 2, don't assume it's custom when it can be a standard protocol. So I spent a lot of time looking at this, reversing it, and like writing in the report in big details what was the proxy, how it was supported. I was interested by it because it supported both SOCKS 4 and 5 and HTTP, HTTPS at the same time. But the SOCKS part was all documented by hand, like, oh, the first byte is this, after there is the IP, after there's the port. And then when we entered the peer review stage of the report, a colleague of mine told me, oh, you know what you thoroughly described is actually a SOCKS proxy, just normal SOCKS. So, don't. I spent all this time writing all that description of SOCKS where I could, so a lot of delete afterwards, delete 2-3 pages, and just, it's SOCKS v4 and v5. So, thumbs up for the design of having authorized IPs only. As I said, we couldn't fingerprint scan the internet because of that. We tried some things with the Rapid7 folks, like if telnet is present and the port is a shut and not a stealth, but it didn't work. Like, we had crazy amounts of hosts. So, good job. Bad job, CNC IP is hard-coded, no fallback domain or no DGA. I know how much we all love DGAs now. And it was not there, so yeah, surprising. So another thing that the Linux Moose does is trying to spread itself through a worm-like behavior. So this is a kind of a rough map of everything it will try to scan. So it will try to scan internet at large, but it will dedicate a lot of threads to scan the closely related IP addresses. So not wide internet, but really close. And we assume that this is in order to find mistakes in firewall configuration, who would block, a lot of the IPs. But if it's inside or nearby in ISPs, for example, then it would be allowed. And in our monitoring, we let the telnet brute forcer run for a few days, and we noticed the success rate of the completely random scan versus the close-by IPs. And we noticed that it is effective. It is something that seems to be bypassing some firewall rules. And again, another thread per each LAN interface where it will linearly scan for telnet all of the subnet. Attack vector is a telnet credential brute force using a word list of 304 user and password entries, which are provided by the CNC. We monitored the CNC for a few months, and the word list never changed. And it was easy to find it on the internet, so they used the list online. Here's roughly the compromise protocol. So what is really intriguing is that the CNC is actively involved during the compromise, which is, again, a design decision that we'll discuss. But so what happens is victim information is sent to the CNC server, and then the CNC sends obfuscated commands with like Bozo crypto. The router performing the infection will unscramble them and then send the commands directly to the victim via telnet. Two different mechanisms to deliver the payload. One was a wget on the end, the router, which means you can do replay attack and then obtain the binary. But the other one was using echo with X escape character, so sending through the middle router a lot of echo, and append on the file, up until when the file would be complete on the victim, and then enabling execution and executing it, which is nice because there's no replay attack. If you don't have full packet capture, you cannot extract the binary. So, good design, it can perform cross-arch infection, meaning a MIPS sample can compromise an ARM router and still deliver the right binary. But if the CNC is down, there's no more infection. So CNC is really, again, a key weakness in this design. And something weird, there's no persistence. It's probably hard to do in a portable fashion. This is something I was told after the virus bulletin where I gave a small talk on Linux Moose. It's true, the flash memory and stuff like that probably makes it complicated, and it's probably the reason why it's not done. And also, they can always come back. They got in through weak credentials, and it was available from the internet. It means that they can come back. And another good design of Linux moves, it literally kills the competition. So it will look for Bitcoin miners, DDoS, anything that will fight for resources on the malware side, and it will try to kill all of these processes every hour. So in a nutshell, this is how the thing is laid out on the purely from our analysis of the sample. So propagation, proxy server, NAT traversal, and also the generic sniffer that eavesdrop on the network. Lessons learned number 3, less reverse engineering, more honeypot. Because we were stuck. We had all this understanding, but we still didn't know what was going on with the threat, what was the goal. So we deployed the QEMU VM in the cloud. So Debian MIPS QEMU image, have it reachable from the internet. Before it was reachable from the internet, we had nothing. Once it became reachable, things really started moving. So we watched it behave and we firewalled it to avoid infecting other people with our things. So if you want some hints, the URL images are already pre-done, pre-packaged. And here's a QEMU command, which is a nice way to use and easy to deploy in the cloud. So you can copy that once the slide will be available. So the lesson that we've learned here was we were too careful. I coded a fake server and had everything done in isolated environment. And in the end, we went YOLO and we gathered a lot of information, and it really helped the analysis. So thumbs up. It was a hard to track malware. We had a hard time reproducing the environment necessary to be able to understand the operation. So moose herding. So it has potential for espionage because of the packet sniffer. It has infiltration capabilities because of NAT traversal and spreading past firewalls. What are they using it for? Fortunately, the first thing we realized it was sniffing cookies for social media sites, which we had preferred more APT type. The first Linux APT, stuff like that would have been nice, but no, social media. And we were like, what? Sniffing HTTPS cookies? Because all of these cookies are now all on HTTPS only. So for us, it was, again, a weird thing, Then we started looking at the proxy usage. So the 10.0.0.73 port that is used. In the next few slides, we will look at the nature of the traffic, the protocol, the targeted social networks. Here in blue, the higher line is the number of requests per day done on the proxy of our honeypot. And in blue is social media network related traffic. In the light blue is other, so there's none, it's all zeros. And in the orange, it's botnet traffic. So a little bit of meta traffic, but most of it was social networks. So even throughout the months that we monitored this threat, we didn't see the operator using it as a VPN. We didn't see any things like that. It was really only performing requests on several social networks. So if we look at the rundown of the protocol, 4% of operator HTTP, 18% of social network, but access through HTTP. All of it was Instagram. All of the other social network were all HTTPS. And the HTTPS allowed us to look at the certificate. Because due to the nature of the SOX proxy, we would only see the IP addresses. And IP addresses nowadays always, or most always, resolve to cloud addresses. So you reach AWS, you're not sure who was the original intention. Was it Instagram? Was it Twitter? Was it another? Or also a lot of CDNs in that traffic. And so HTTPS enabled us, because of the certificate and the CN in the certificate, to understand what social networks were targeted. And here's a rundown of the HTTPS traffic. So on the right-hand side, you see an extrapolation of the 3% of others, so don't get fooled by that. There's a very little Yandex. It's not a big part. But so the biggest social network targeted was Twitter and Vine, which the C names are like colliding. Instagram second, and then others like YouTube, Yandex, Yahoo, and quite a lot of SoundCloud also. So yes, a lot of HTTPS, but we digged into the HTTP that we saw. This is the only HTTP traffic that was available was, as you can see in number 2, an upgrade to HTTPS. So the only thing we had was the location of the first hit, the first get, if you want, in number 1. And this is how we based the following slides of what we think it's doing. So as an example, we looked at one of the user that was fetched, and we tracked it through time. So the pattern was they are created, and then a few hours later, there is around always below 50 that the accounts that was newly created follows. And then we looked at what they are following, and we noticed that they follow each other, so a lot of cross-referencing. And once in a while, they will follow some accounts which looks more like either business or models. There were a lot of traffic around modeling. And so in this case, Signé seems to be a kind of a wedding type business. So we looked at it when we first saw it. It was they had 3,000 followers and only 7 posts and following 7 people. And they have no internet presence beside their Instagram. So it's not oh, we have a big business and we launch something on Instagram on the side. It's more the other way around. Instagram seemed to be their main operation. And then 1 week after, so we went from 3,000 follower to 11,600, adding a few pictures and following 1 new account, and still no big internet presence. So for us, it was enough evidence to, we did the best we could, but enough evidence to assess that it's probably a botnet that is used to do social media follows, like views, and stuff like that. So fraud hidden in HTTPS, good job, because this really make our job of assessing impact and convincing people it's important harder. The proof is not as strong as it could be. Except Instagram first hit. Sorry guy, you forgot this one. So in a nutshell, what we have in the operation is stolen cookies, social network fraud, and focus on reproduction, spreading. These are the operation done by the thing. And in here, the victim, the guy besides the router, is not really a real victim. And this is why the botnet might not be as interesting for as a takedown or whatever. As soon as you reboot your router, it's clean, right? Because there's no persistent mechanism. So what happens when your internet goes bad or you don't understand? And for example, what will happen in this case is the router will run out of memory because they spawn 35 threads and they do all this kind of stuff. Memory management is minimal. So what will happen is you will start having problems with your internet. You reboot your router, you're cleaned, and now you can move on. So no one. It's really designed to stay under the radar, it feels. So latest developments. The impact of our white paper. A few weeks after the publication, the CNC went dark. I was in contact with the hosting provider, and I was trying to help to try to have access to the IPs. I really wanted the IPs to assess the botnet size and the impact. And he told me, oh, it's compromised, it's not malicious, I'm sure. I said, okay, cool, can I help clean it? I will do it for free, and I will rent you a server, we will move on the side the infected guy, and I will install, take care of I will rent a server, install the old IPs in it, and then just, gather the traffic. But it didn't happen. I stopped hearing from him until we published. And then when we published, he came back, oh, sorry, I was on vacation for a long time. I forgot to reply to your email. And then we were again close to have some kind of arrangement. And again, he went completely dark. And at the same time, this is ISC, Internet Storm Center port probe of the internet. So this doesn't mean much, but it's still probes that they have deployed everywhere on the internet that can roughly tell you the volume of traffic that they saw. And this is beyond, internet noise, because internet noise looks like this, the July to September part of the chart. And so what happens is that the few weeks I was in contact afterwards, and then at some point they probably for real cleaned the machine or removed them. But unfortunately, I couldn't get access to the IP addresses, so again, no measure of impact. So this is activity on the port 10,073. So afterwards, I was on the lookout for Moose version 2. So I knew, or I expected, that they read the paper. And I knew that they would, some of the stuff that we said, they would try to avoid it. So that my Yara rules, my hunting rules must be like trying to plan ahead, to beat the guys, be cleverer than them. But I still looked at a ton of samples because I expected them to UPX the whole thing, and so defeat the Yara rules, but still, have it like stay the same. And at some point we found an update right before virus bulletin. It's using a new service port as was expected, since it was highlighted like this in the report. They added a CNC selection on the CLI. So the CNC server is no more in the binary. It's when the malware is launched, and since it has CNC cooperation, as we saw in the compromised slide, it will be able, it's packed as an integer and it's slightly obfuscated, so it's XORed in the code, and it will use this new CNC. Another thing they did is the server returns a 404 on unknown hosts. So I was able to get a sample. I was able to get the integer that was used to launch the sample, but I tried recreating an environment from a different IP, and the CNC just never responded to the request of my new fake client, if you want. So we're still trying to get infected at this point. Now I have like open honeypots trying with some passwords that I know were in the list, trying to be infected by this threat again. And the goal is to this time do man in the middle of the SSL traffic and try to see if the bot will still connect. So reading research paper and adapting, thumbs up, malware operator. If we look at the traffic of the new version, you can see that they had their kind of a vacation for the summer, and then they kick-started in September the new version. So this is the port analysis, the previous botnet, and the new port of the new version. Some takeaways. We released some research artifacts, so Python and shell script. Protocol dissectors, the fake server code I've written, a lot of it is T-Shark wrappers, and Yara rule and IOCs. Everything is in the ESET's GitHub. I know it's not of huge value, but anyone like looking to do a more network type analysis and research, I think the T-Shark stuff is pretty decent. And I'm more of a network background and really familiar with these things, so it might be some inspiration. And if not for professional, at least for someone who is trying to get started. Another takeaway is the embedded Linux malware is not yet complex, but still the tools and the processes needs to catch up. The Windows stuff is definitely more complex, advanced, and hard to track. But we have absolutely no visibility, and without visibility, we have a problem saying the impact or the number of infected hosts, which makes it really harder to have a good case and help convince people of the importance of the threat. It is still a low-hanging fruit, and prevention is really simple. Like right now, what I started doing is every time I get into a new network, I look the web administration interface of the router I am connecting to. And if I can get in, but of course I do this at friends' home. I don't do this in public settings. But if I can get in with admin, then I change the password, take a post-it, write down the new password I chose for them, and put the post-it on the router itself. The threats are doing this from the network, from outside. If you have physical access anyway, you're screwed. So I think this is just a good mean to raise the security and the awareness of people around you. So yeah, I would say, like, friends don't let friends run routers with default credentials. Any questions? Oops. Any questions?
So questions if you want to see the underwear again?
Yeah. Stop there. Sponsors are more important.
Okay. Really no question? Wow. No, over there. Power is back on the right side.
I was just thinking, like, would you suggest that maybe people should have some kind of AV running on the router to prevent this in the future, or at least, you know, detect it earlier?
So is it F-Secure or who released the new kind of router who will do F-Secure? So there's a new device, you know, who will do Sophos or F-Secure? F-Secure Sense. So you see that some people in the market are trying to address this problem. Another thing that ESET is working on, and I know Avast also presented about it at VB, is from your host, your AV is trying to connect on your router and verifies if it's vulnerable and sends you pop-ups and suggests you to patch it. There are legal, you know, potential pitfalls, but I guess if you're already choosing correctly between home network, business network, and, you know, public network, and the AV uses that information to know, okay, it's home, I can scan and warn you that you have default credentials. I think these are, like, of course, it shouldn't have come to this, like, this bad, but I think it's a fair solution. But running security solution on routers, I don't think is realistic.
Hi. My question goes to the development environment type of thing. So you said you had a bit of a hard time to reproduce this development environment. Do you think there's a lot of variability in this development environment? And second sub question, so to speak, is have you checked if there's like artifacts between the first and the second version of that threat that you've seen, which make you like infer their development environment, things like GCC versions or something like that?
So for the first version, we saw, I'm pretty sure that they're running the OpenWRT toolchain, which makes it pretty, you know, reproducible and easy to build not the samples, but the right libraries and everything. For version 2, I haven't looked too closely at it because we can still bin zip from the previous version to the new version. There's a lot of noise, more noise, but still we don't want to do an as thorough job as we did on the first time around. So I haven't looked at it deeply enough, but in a general sense, since all of the embedded samples I looked at, of course, it's crazy the degree of variability. You know, there are, I don't know, at least 10 projects who are bootstrapping embedded code initiative. Some target really low memory environments, some target bigger environments, and like the vendors are also have all their own SDKs. So if you want to target specifically TP-Link or Belkin, you can. So it would be nice to have some kind of a project who would try to map these things and do something about it. Definitely, it would be worthwhile, I think.
Thanks.
Last minute question. Okay, thank you.
Merci beaucoup.